Oh, it just started.
All right. It is kind of weird since nobody's here. Only Mark is here, right?
Yeah, also there's a lot of power outages and stuff. So.
True. Okay, let's just solve this. So this is our first question that we're gonna. This was one of the retake from last semester's. Can you all hear me okay? I'm having something bad quality.
You sound like you're cutting up right now.
What was that, Nicholas?
You sound like you're cutting up. It's kind of hard to hear you. It's like every other second or.
Okay. It says I'm having bad network quality. Interesting. Ton, do you hear me well, or am I cutting off?
Oh, you sound better now.
Okay.
Yeah, you are cutting off.
I'm cutting off right now? Hopefully we can see the recording then. Right. Okay, the first question here is, we're given a transmission line with internal impedance with 50 ohms with a characteristic impedance of 50 ohm lossless transmission line. This is a fairly straightforward question, but the length of the transmission line is 13.3. It's 13.3 lambda, where lambda is the signal wavelength. And it is connected to a load ZL, which is not given. That's the first question. We need to figure out the load impedance. And what we are given is the Z in, which is 300 minus J25. So the first problem, or the first question here, is how do we actually solve for the impedance, the load impedance, ZL? How do we solve for this? Okay, I think we have a couple of more joining in, so that's good. So let me ask you guys, I think you guys do know how to solve this, right? I think we have solved a lot of problems by now. So what's the first step, if I may ask you guys?
I believe there's an equation whether you're using cosine, sine, or tangents with the z0, the impedance not, which is I guess 50, I think, and the input, and I believe that's how you. I believe that's how you get input or something like that, or not input.
So if we are given the input impedance, then we could use the formula for input impedance to actually solve for ZL, right? So that's what we are going to do in the first problem. So there are a couple of formulas to do so. What I'm going to use is this one. So this is straight from your book. Z in equals Z naught, 1 plus the reflection coefficient times e to the power negative j 4 pi L. Are you guys familiar with this formula? I'm hearing no feedback. Have you all seen this formula, or is there a lag?
I've seen a formula of this in the book, yeah, and I think there was one homework that used at least half of this equation, something like that.
I think you can either use this, or we could also use the other formula that we have for the input impedance, which is the one that's fairly easy to remember. You can use this, or you could possibly use the other one, which is basically this, right? 2 pi, this is actually beta L. Tan beta L. So you guys can use either one of these formulas. They both will work. what we have to do is basically solve for ZL. Here, you guys are basically solving for the reflection coefficient, and we will basically solve for ZL by solving this equation later on. This actually makes the math a little more easier. That's why we're going to do this. But you guys can do any of these. They'll give you the same answer. Bro. Okay. Are you all following along?
Yeah,
Team,
straightforward so far.
Drew,
Yeah. Thank you.
Patrick. All right. All this for now. I'm going to erase this. Z in. I'm going to send this guy over there. I'm losing you guys.
No, you're just splitting up the
Now-
equations.
Yes, correct. All right, now I'm just gonna coefficient at one side, everything else on the other side. So just Z in times Z in. Let me not skip any steps today. Or let's pull this guy and this guy at the same side. Equals. This is all straightforward, right? Am I losing anyone? Hopefully not. Okay, the next step is fairly straightforward. Oh, when I was giving these exams, the main culprit usually was whenever I was putting things into the calculator. One time I just put a value wrong in the calculator, and Dr. George really cut a lot of points off, because sometimes all these questions are interconnected. So if you find this value, you might need this to calculate something else, like the load voltage later on, right? So make sure whatever you're plugging into your calculator is actually the right value. It sounds simple, but since the numbers we're calculating are complex, and even a plus or negative sign can really matter in. So let's solve this for the reflection coefficient. That would be Z in minus Z naught. Do you guys have your calculator out? I'm gonna need one of you all to solve this for me.
Yeah, we calculate 1 moment.
All right. So Z in we have is 300 minus 25J. We have our Z naught as 50 ohms. And L is 13.3 lambda.
And so the one real quick question for that the 4 pi L. Usually with the beta L and the other equation, we can cancel out the lambdas. For this, there would be a leftover in terms of lambda, or would that cancel
Wait, no.
out?
So this one, it's already solved for lambda. So this is just 13.3. The L over here is just the length. It's not the lambda. You don't need the lambda carry over here. You could actually say this is just Z, I guess.
Gotcha. Okay, I have negative 0.59 minus 0.5 0.40J.
0.59 minus 0.40J. Okay, that's our reflection coefficient. Now we solve for what we're looking for. How do you actually solve for the load impedance? What is the formula for how do we actually calculate the reflection coefficient? Anyone? Drew?
Yeah. Well, we calculate the reflection coefficient with ZL minus Z naught over ZL plus Z naught.
Of course. I know you know that, Nicholas. All right. So let's solve for ZL now. So are you all following along with my math here?
Yeah, I'm just entering in the calculator.
That's good. Okay, so let's just plug this back into the calculator and see what we get. Is anyone putting the numbers into the calculator? Let me know when you guys are done.
Yeah, I got 9.149 minus 14.88J, but I did simplify the 0.59 and negative 0.04, like 0.40J. I didn't put like a bunch of part of the decimals, you know. I
Sure.
just
All right.
kept it
That's
kind
the correct answer. So that's our load impedance calculated from the given input impedance. Pretty straightforward. Okay, that's good. So did everyone follow this question along? T and Drew and Patrick, how do you guys feel about that problem?
I got it. Thank you.
Yeah, that makes sense.
All right, that was pretty straightforward, right? Wow, test one postponed, actually. Wasn't that the email from
More
EMAG?
time to study.
To minimize adverse effects on your study ongoing extreme cold. Wow, a very good time to have that email, right?
One more week. Yep.
Awesome. All right, the second problem we're going to solve is how do we calculate the time varying voltage V of L? Since the stress is gone, let me just ask you all how to do this. I will do whatever you guys tell me to solve. How do you actually solve the time varying voltage here? Time varying, it's load voltage actually. Basically this guy over here. This is in the phasor format. We need it in the time varying load format. It's a function of t. How do we actually solve this? What do you guys feel? If this was your test, what would your first step be right over here?
I would assume to. I thought there was some sort of equation for it. I'm not really sure. I mean, I can. For some reason, my mind goes first converting things to polar,
Sure,
but I don't
that's
remember
right.
why.
So we are given the generator voltage as a function of t, right? As a time varying voltage. So we can go ahead and convert it to a phasor because we don't have any phase angle given. It's basically just 100 volts, right? That's our first phasor. Now what do we do?
And there's a table that shows like if you have phasors, like what format, right, to get the phasor. So, isn't that right?
There is, yes.
So what's our next step, Mark? What would you do in your exam if this was your problem? So I think you guys are given an equation for a voltage, right? An equation for voltage that basically solves for the voltage at each point in the transmission line. Does anyone remember that formula? Let me pick on somebody. Drew, do you know how to do this? Do you know the formula for voltage on any point in the transmission line?
Is it the V of Z equals V, like not plus
Correct. That's the one I'm looking for.
the e to the negative j?
That's the
Like-
one I'm looking for. You're
Okay.
right. So let me actually make sure I'm copying the right one. All right. So we have the formula as it's V of Z phasor equals VO positive e to the power negative j beta z plus the reflection coefficient times e to the power j beta z. All right, that's the one we're looking for, right? So if we know all the parameters to this formula, we can basically solve for z v of L, basically, right? But what are we actually missing here? What do we need to actually solve this equation? What parameter are we missing? Patrick?
We're missing V naught plus, right? Like,
Correct. So we are missing this value. So our next challenge is how do we actually compute this from all that we are given?
is V phasor of Z the same as the phasor of VGT, or is that just the phasor of VG?
Which value are you talking about?
The phasor of VG of 100 that's not the phasor V of Z, right?
No, this is Z. This is generator voltage, and Z is the Z here is basically the length. Length as in the parameter Z, right? Let's see. This was the VG, and this one is VZ, basically.
Yeah, the length of the transmission line Z only considers like the transmission line outside of the generator network. So like if it's got Z as a function, you know it's part of the transmission line, whereas the generator has its own voltage.
Okay, let me test you guys one more time. How do we solve for V naught plus. Have we solved? I know there's a lot of equations and it's kind of gets messy in the first exam, but just try anything out. I'll give you the answer eventually. So what would you guys do if this was your exam? How would you solve for V naught plus?
I got one equation that I think it may be the V naught plus equals the V of G phasor times Zn all over Z of G plus Zn. Like that one. That one's times the 1 over the E negative J beta Z plus R. Like reflection coefficient.
So was it this guy over here?
Yeah, that one. And we'd still have the E's with the reflection coefficient or gamma, whatever it's called, but it would be 1 over that value. There's an equation for that.
This one. Okay, I remember this. So can we solve for this one? Do we have everything we need to solve this equation? We got the VG. We have this value. Zn as was actually given in the problem itself. So we have this. We have this. We have this. The length. We have this. And we actually do have everything to solve this equation, right? Okay, so that was correct. Good job, Mark. The only thing remaining is to plug it back into your calculator, but we actually have a value to move forward with. So let me scroll all the way up so you guys can plug it into your calculator. Actually make it a lot simpler for you guys. It's 100. Z in was 300 minus J 25 minus 25J. 300 minus 25J plus 50 times. This is the part I actually made a lot of mistakes on. What is L over here?
So the beta L will go down to 2 pi times 13.3.
Correct. 2 pi times 13.3 plus the reflection coefficient we calculated before. So we gotta look back to this value. Negative 0.59, negative 0.4J, e to the power negative J 2 pi times 13.3. Okay, now that's what you guys are solving. Usually what I've found that really helps to make less errors are to use polar format, polar values instead of these rectangular values. I actually do that a lot, so I don't make a lot of mistakes when I'm actually solving these equations.
Okay, I have the answer in rectangular and polar. Okay. Rectangular is 0.201 minus 0.225J. Polar is 0.302 times E to the power of negative 0.842J.
842J. Let's see if that matches the one I had. We are basically solving for VO naught, right? This actually does not.
Not plus. Okay.
Does not match to the one I calculated before. Let's see where we got wrong. Did anybody else also solve this?
Wait, no, I used the Z of L for my for the R instead. I mean the gamma. So once let me put that. I think I'll fix it. My apologies for a second.
while it seems easy, it's always very easy to mess up while plugging things into your calculator. Believe me. Especially in this class. Did anybody else solve it? Tian, are you following along?
Yeah.
So did you plug it into your calculator as well?
Yeah, but I'm not doing that particular way.
Okay, that's fine.
I do have the new answer that I think is right. I think it's a 0.6367 plus 3.48J.
And what's the one in your polar?
For polar, it is 3.542 times e to the power of 1.39J.
It still does not match with what I got. So most of the time when you're actually solving for these values, it's actually surprising because most of the time you'll have like very solid quantities like solid 40 or solid 10. I mean, these are good numbers, right? No decimal points or anything. So the answer for this problem also comes at a solid value. But let me see. Let me plug it into my calculator again and see if I actually solved this right.
Yeah, I'm taking the old R and make it polar and see if that fixes it.
Did I actually call 300 minus 25J? I think I did everything. I should have done everything correctly. Let me plug it into my calculator and see what I get. The reflection coefficient. You could have messed up here as well because this is one value.
I think I have the let's see, let me see if it's the wrong e to the negative. The first one I think I have negative instead of positive, and the second one I have negative. Let's see if that fixes it.
Okay.
Let me just tell you real quick and see if that is this is the correct value. So with the negative swapped, I got negative 0.86 minus 2.78J for rectangular, and polar was 2.91 to e to the power negative 1.87J.
So one way to like actually think about that you might be doing it wrong is since the generator voltage is like 100 volts, right? And if you're saying the absolute value of your VO plus is less than 1, basically, it's 0 point something, right? That's a clear giveaway that you might be doing it wrong because that's too low. Going from 100 volts to a very low value around even less than 1, so that's a clear giveaway that you might have plugged in something wrong in your calculator. Let's see.
Okay, what did you get? Because I have one when I just double checked the 100 and I got like to 29.14 times e to the power negative 1.87.
What I actually solved earlier was this value, and in the rectangular I had negative 15.45 minus 47.5J. This is what I solved earlier. Let me see if I actually did everything correctly though. Plug it in. Also, do check that your calculator is in radians, not degrees. That messes up everything. Yep, I still get this. So are you plugging in everything like I did over here, Mark? Because I still do get this value. A couple of things.
Yeah, I want to see if I 1 second. I'm rewriting it from scratch.
So you got to make sure your calculator is in radians so that it can calculate this value correctly. Make sure.
Okay, yeah, I do have the 50 to e power negative 1.885 j, which is a rectangular for negative 15.46 minus 47.549 j. I think I just needed to rewrite it from fresh. There's something wrong with it. I didn't notice.
All right, that's good. So we actually solve for the VO plus, right? Is everybody following along to this point? For those who did join later on, what we are basically solving for is this problem. We have a transmission line, we have a load, we calculated the load impedance from the input impedance in the first problem, and now we are solving for the time varying voltage at the load. And we managed to calculate the VO plus, right? Now what do we do? How do we actually calculate the load voltage?
Just bring it back into the equation, right?
Let's just do that real quick. Let's just say V of L now. At the load, what's your Z value? If you are at this point, what would your Z equal?
0.
Like Z equals 0 at this point, right? That would make this equation a lot simpler because we have a lot of Z's here. They all go to 0. So V of L equals, let's keep this as it is, e to the power negative j. Now this is 0, so basically this is 1. Let me make sure I'm not losing anyone. So this goes to 1. This goes to 1 as well because e to the power 0 equals 1, right? Just one more calculation in your calculator. Let me know what you get.
Polar is 28.75 e to the power negative 2.66 j, and rectangular was negative 25.5 minus 13.19 j for me.
You said your polar was 28.75 e to the power negative 2.66 j?
Yes.
Okay. So if we have it in polar, are we done? Do we have our load voltage now? Can we stop working on this problem? What do you all think?
Do we need the? Yeah, we have the load of T.
So it's a very simple mistake to make, and I'm pretty sure Dr. Joshua will actually take negative 5 points away if you do that, because the question is actually asking for time varying voltage, right? And if you leave it in phasor, that's not where you actually still need to go one more step.
So we go back to rectangular.
Yeah, not rectangular, but you got to convert this polar to in terms of t, time varying as a function of t, basically. And this should be pretty straightforward because converting from polar is usually a lot easier. It's basically 28.75 cosine of omega t minus 2.66, right? That's your time varying voltage. How do you actually write it into VL of t? All right.
Write out the like taking the real part times e to the j omega t, because I know Dr. Twacha likes to see that too.
Which part?
Like just taking the real part of the phasor form times e to the j omega t.
Yeah.
We'll like put in RE.
So what Easton is saying is actually show the steps to convert this value. So if we have V of L equals 28.75 e to the power negative 2.66 j, to convert it, we basically take the wheel part. You can take 28.75 out. Wheel part of e to the power negative 2.66 j. That would be your Euler's formula will be cosine of omega t minus 2.66 plus j sine omega t minus 2.66, and basically if you take the wheel part out, you get this value, right? So have I lost anyone yet? Okay, I hope that was straightforward. Did you all follow along? Was there any problems with this particular question?
I'm good so far.
Okay. Finally, our last questions ask for compute the time average power delivered by the generator PG and the time average power delivered to the load PFL. So do you all know how to solve this problem?
Mostly, it's like power is like 1/2 to the absolute value of something squared, just depending on what you're looking for.
Correct. That is correct. I'm gonna actually let you guys solve it. I'm gonna write out the formulas, and let's see if you all do get the right answer. So your power from the generator is basically given by 1/2 of the wheel part of the generator voltage times the current that's drawn from the generator, but you got to take the conjugate of that. It does seem very straightforward, but you really mess up when you actually plug it into the calculator. I don't know how, but even I do it sometimes. PFL is given by the load voltage, which you guys just calculated, right? Times the current that's actually drawn, again, conjugate. So this is an exercise basically of plugging things into your calculator. So let me know what you guys actually solve here. I'm going to give you 5 minutes to do so. Let's see if you all do get the right answers from your calculator, basically, just plugging things into your calculator. So I want everyone to do this, actually. It's a good practice to plug things into your calculator, especially for this class.
And what you mean by the conjugate for the IG and IL value, like how we got those, like it's like the 1 over whatever impedance we had, right? Like so 1 over ZG. Something like that, maybe.
So conjugate is basically if you have a rectangular complex number as like a plus jb, then the conjugate is basically a minus jb. Right? It's just the imaginary part. the sign changes.
Or if it's in polar, you can just make the angle negative, I think.
If it's in polar and it's like negative JB, then the conjugate would be e to the power positive JB.
If you're not sure, Mark, and you have the Inspire, you can type in the conjugate like CO and J and put in your value.
Like literally just type CO and J, or is there like the book button?
Yeah, you can type that in and it'll autocorrect it to like the formula, and then you'll put your like equation in the parentheses.
Or you could go to menu to number and go to complex number tools, and there is a complex conjugate at the first option, the first menu.
No.
I'm hoping everyone is plugging things into the calculator at this point. Let me know if I need to step in anywhere, if you guys are confused on how to calculate the current or the conjugate.
I was thinking about the current. I was thinking like I was just to do the like the voltage over the impedance or whatever. Something like that.
Yep,
I was
that's
thinking,
right.
Yeah.
That's basically it. All right.
Wait, but to get the current, is it because you use like the input current, right?
For PG, yes, the current that's drawn from the generator. So basically at this point right here, the II basically. And for the load, you basically have to solve for the I of L.
Well, I think essentially it's the same. So if you use I think it's the same. It gives the same answer for either if you use I in or IG.
Yeah. Did anyone actually solve it yet?
No, because because V of G phasor is like 100 and the conjugate. I was using 50 because that was Z of G, but he said Z of N works just as well, which is probably the right thing.
Couple of more minutes to do so. What was your question again, Mark? I think I missed it.
Like, so I have I have 1/2 real, like 100 is the V of G phasor, and I of G for equivalent would be the 1 over. I thought it was going to be Z of G, but Z of G is 50. And someone just said that Z of G. I mean, that impedance is for this one as good as just having the Z of N, which is the.
So for
300
the I of G, the impedance here. So the current here would basically be, so you're looking at this point, right? So your impedance at this point would basically be Z of N. So you're right. So the current I of I or I of G would basically be V equals IR, right? So I will be V of G basically divided by Zn.
Okay, well I got using that I didn't square nothing.
Actually no. It's Zn plus Z naught.
Zn plus Z naught? Oh,
yeah.
Okay.
Because at this point you got a not Z naught but ZZ, this value, because you're at this point, right? Because at this point, at this particular point, your transmission line is looking something like this. You have your Z of Z, and you have your Z in. It's looking something like this, right? You have your V of Z. So you're basically solving for your I of G, or the current over here. At this point, at this particular point, if you just use what you learned from circuits to calculate your current, it would be V of G times Z of G plus Zn.
Okay, so yeah, for the real value of that over 1/2 real value of VG, or the conjugate of Zn plus Zg, I got 0.142 watts.
So the real value you got was how much?
0.142 watts. I just like that.
Again, this looks awfully low, right? Anytime you're getting a value below 1 or very small value, you got to be aware that something might be going wrong. And also for power, if you're getting something like that's negative, that's a clear giveaway that you might be doing something wrong again. But here, since we're supplying with 100 volts and getting some power that's awfully low, we could be doing something wrong again.
Is the real values, aren't they supposed to be squared or something? I don't have the formulas with me, but I thought they were, or at least one of them. I think maybe it's just been current squared.
I don't think it's the current squared, but it's just the conjugate, as far as I can remember.
Yeah, and I have conjugate in there. I don't know what I did wrong for this one.
What value are you getting for IG?
For IG, I just did so what it says in my calculator is 1/2 times real, like the math function you have for real, 100 divided by the function in TI of conj parentheses 300 minus 25i plus 50, which is the Zn plus Zg. I think.
Okay. Did anybody solve it?
Yeah, it's 14.21.
That is correct. 14.21 is the right answer. So what I wanted to portray was, even though this is just a straightforward plug it into a calculator kind of question, you can get it wrong because there are a lot of things to consider. You basically need to practice plugging things into your TI calculator. Things might go wrong, even though you know how to do it. It's just what you get out of your calculator might be wrong because you do need to pay a lot of attention in a lot of things. All right, you guys need to do the same thing over here. Mark, did you actually get this value for the generator power?
No, I got 14213. Like I got it. Like if I make the numerator 10,000, then I match up. But for the 100 for the VGG phaser, it doesn't match up for me. Like I have just 1/2 real times.
Let me actually solve it right over here.
Yeah. Like I can try to see.
Equals 1/2 the real value. VG is just 100. IFG that we just said over here is 100 divided by Z of Z is.
So okay, why are you why is it times the 100 again?
So
wouldn't it just be like a 1 over that value? So it'd be just 100 over that. Why is there another 100?
If you can see this point right over here, we just defined IFG, right? So this is the circuit we have at this particular point. We're at this point, right? At this point, we have a Z in, the input impedance at this point. We have our Z generator impedance over here, and we have our voltage source. So this is our equivalent circuit. And if you just apply your circuit theory knowledge, then your current would be basically, so your current is V equals IR, then your current would be V divided by R, right? So your current is the generator voltage divided by the total impedance.
Okay.
And I just apply this value again. So our current is, again, the generator voltage, that's 100, ZZ plus Zn. This is 50, and Zn was, what was it? I keep forgetting it. 300 minus J25. 300 minus J25. Now, important thing to remember is do not forget to conjugate this particular value over here. If you plug this guy into your calculator, you should get something. Let me see my solution. Actually, I didn't solve for it. All right, let me plug it into my calculator. If you apply that guy into your calculator, you should be getting J25. Basically this 0.2849 e to the power 0.071 j, and conjugate basically means the same thing. So you basically conjugate it. That means to apply a negative sign here. Take that out. Now just plug it into your calculator, take the real part, divide it by 2. You should get 14.21 watts. This question was actually worth 20 points, so it is a lot of points just to plug things into your calculator. Even though it sounds easy, and even though you do know how to do it, there's still a lot of places where you can mess up because you didn't plug the right value in, or you didn't set your calculator in radians or something like that. So I just want to say that you guys need to be very careful while plugging things into your calculator. Did anyone solve for the power delivered to the load?
Yeah, it's 12.4, 12.1.
I think it's about right. What I got was 12.18, but since we are running a lot of values, I think that's right. It is 12 point something, so that does make sense, right? So the power delivered by the generator is this much, and the power at the load is a little less. That's reasonable. Okay, so that was actually everything you needed to do for the first problem.
What was the power generated by the load?
I solved it for 12.18 watts, but anything around 12 should give you full credits. You are cutting off all your decimal points somewhere. So it's 12 point something, you can say.
Okay, yeah, I got 23.63.
All right, it does seem like you
Yeah.
need to practice plugging things into your calculator.
Oh well, what was the because I used yeah, I don't know what's yeah.
Yeah, if you were at the last reviews, I probably sound like a broken record, but like I knew how to solve these problems step by step, and I had the correct answers in front of me, but I was reworking them ahead of the review we did on Saturday. It literally took me like over 2 hours because I kept missing
Same.
J's in my calculator and stuff. Like writing a code is going to save your life. Like something that already has all the J's and stuff in there, and like you can just put in your values. Like even if it's not a code that'll just solve the whole problem for you, like something where you just have the equations where you can just use them.
When I was actually giving my test, we actually had to go to class. So the best thing we could do is actually program the TI Inspire, basically write functions for the TI Inspire and basically plug in all the numbers to that function, and it gives you the value out. That makes you not mess up during the exam time. So if you're writing the entire formula into your calculator, right? So imagine you're writing this guy during your exam, and you forgot this negative sign, just this negative sign, then your answer is wrong. And if you did not show any steps on top of that, then you might actually get 0. That sucks.
Can you write up the steps for the power of the load so I know what I can possibly have done wrong or know what it's supposed to be?
Sure. Power of the load. Power of the load is 1/2 wheel of the VFL that we calculated and IFL conjugate. So let me ask you, how did you calculate this guy, IFL?
For IFL, I added as VFL over the conjugate of the Z of L, so it was like 28.755 e to the power of negative.
Wait. V of L divided by the Z of L conjugate, or the entire value conjugate?
Yeah, my V of L was 28.755 e to negative j.266, and my
28.75, right? Okay.
Yeah.
What you have?
Yeah, and the Z of L I had 9.1495 minus 14.88 j.
And Z of L, yeah, it was right here.
Yeah.
Plug that into your calculator.
Yeah, it was conjugate of that, the 9.1, thing, but yeah.
And
is it conjugate in the whole thing, or just the denominator?
The whole thing.
Okay, that probably is it. 1 second. That gives me 12.936 watts.
All right, that's it. If you solve this question correctly, you're already 50 points ahead. So that's good. When we were actually giving this, we didn't have any reviews and stuff, so we were just all solving whatever we had, but we didn't know if that was the right answer. So right now, it's actually good for you guys because you guys have had, Dr. Duarte did a review. You guys had a review on Saturday. That's 3 reviews by now, so that's a lot of resources. I really do hope you guys do good. Okay, the second question is going to be solved by Nicholas.
Yes.
And I'm going to stop sharing my screen now. Okay. But before I do you guys have any questions related to question number 1? Anything at all? This was actually the easiest question you might get. I think you will get one easy question and one hard question. Calculating the ZL, straightforward. Calculating VFL, straightforward. Calculating the generator voltage is also kind of straight. It's basically plugging into your calculator. So this question is the straightforward problem you're going to get. The second one is kind of convoluted, but you should be able to do it with enough practice. All right, I'm going to stop sharing my screen and hand it over to Nicholas.
Okay, so I'm going to work on the second problem from this test. Let me see here. It should be showing my second screen now. Let's see. Is it? Can you guys see anything?
Yes, we can see it.
Okay, so this is the second problem right here. So what we're doing is we're once again solving a transmission line, but we have 2 loads. And so I'll let you guys look at the problem if you want to save this so you can look at it yourself or write down.
Speaking of that, is it possible for us to get PDFs of the review that was done on Saturday and then this one as well?
Yes, yeah, we can get you those too as well. Yep. I think Easton's here, so he might be able to get you that right now.
Yeah, I'm on the blackboard from what we were writing on, so I can take some screenshots.
Okay. So with this problem, what we're going to find is first the generator voltage. We're not given that. Then we're going to solve for the power at the generator, and then we're going to find the reflection coefficient in the transmission line. So in this step, what I like to do first is I like to write down the values of my locations. So let me know if you guys can't see it. let's see here. So 4.9 lambda, and then 6.65 lambda. Okay. And now we notice something that, seems uneasy to us, right? We're dealing with positive values here of distance. So we want to convert this into the negative values of distance. So what we'll do is we'll set the load, which is what we have set our distance to, as 0. And then what we'll do is we'll figure out this distance right here. So 6.65 minus 4.9 is 1.55, I believe.
Before we do so, can anyone tell me why we're actually converting from the x to the z coordinates? Or basically, do you guys know? Do you guys understand why we're doing that?
Yeah, because it's the convention that Dr. Tuwaja has taught us from the derivation, so we want to put it in a familiar form and have it to where our values are negative, so because that's how we put it into the equations.
Correct.
Mhm.
That's it.
Yep, that is correct. Okay, so now that we've set this guy to minus 1.55 lambda, we can just use the same value for XL over at the very end, because it's the total distance. It'll be 6.65 lambda. Okay, then the first thing I like to do is I like to break this up into 2 transmission lines, each with their own generator. And it really is the equivalent thing. Since we're given a voltage right here, I'll mark it as 0.5 lambda. I'll mark it also down here too as well. We have to use this voltage at that location to solve for V naught plus. Because every time we're solving a transmission line, we always want to find V naught plus or possibly I naught plus so that we can get an equation for the entire length of the line. So first we'll solve for gamma in this transmission line. I'll draw it out for you guys right here. First transmission line. ZL and ZM. And we know the length of this right here is 1.55, or excuse me, yes, 1.55. Oh, sorry, actually, I accidentally wrote that down wrong. It is 1.75. 1.75 lambda. Let me correct that right here. And then 0. Okay, we'll solve for gamma by finding ZL minus Z naught. We discussed that in the last problem, correct? You guys are familiar with this equation. And does anyone want to solve this value for us real quickly? Using the given load and given Z naught?
Yes, one moment.
Okay.
I got 1/3 J. I don't know if that's right.
That's correct. Yep. It's this problem when you see something like that, I wouldn't be like afraid to get this because this seems very simple. It's very, very nice and easy to deal with right here. Okay, and then I'll mark this right here. Okay, so what do you guys think we need to do now after we found gamma, our reflection coefficient? I know that we said we need to get V naught plus. So how do we do that here?
Isn't it the same formula we used from last time? With the sorry.
Yep, you're right. And then what do we use for the voltage? What do we use since we used Vn? What do we use instead?
We use VL.
I think you're almost there, right? You're thinking of this voltage right here, correct?
Yeah.
Exactly. Yes, that is the voltage that we use. So we'll write this down as, in our case, since we redefined our lengths, we'll just write this down as minus 0.5 lambda. And then this is just a special form of the equation that I like to write. It kind of compacts things down a little bit. The tricky thing about this is remembering the 2 right here when you're trying to get everything written down. Okay. And then let us figure out what this guy right here is. So we can convert 3 cosine omega t to phasor. Anyone know what that is?
Isn't it just 3?
Correct. Yep, it is just 3 in phasor form. Okay, and so now that we have this voltage at this location in phasor form, and we're solving for V naught plus, which is also a phasor, or is it just the magnitude as well, we can then solve for V naught plus. You guys, I think you should be able to solve this pretty easily in your calculators. If you want to, you can solve it right now. And if you guys want some word of advice for these types of problems, in this case, we're given a voltage between 2 loads, but in some problems you may see like a voltage like in this case beyond ZM. You might find a voltage right here, and you might have to use like some way to combine stuff that we'll get to in a bit to get up to this point where you can solve for a voltage. Have you guys solved this yet?
So what can we do about that V phasor of the negative 0.5 lambda? I don't see how to.
I guess it wasn't very specific. Sorry. What I wanted us to do was I wanted us to recognize that V naught plus is equivalent to the voltage at any location, just some voltage, right? And then it's divided by partially the wave equation, so that you can get the voltage right here. Say this is Vi of x, right? This is equal to V naught plus e to the minus j beta, j beta L. And then this is plus V naught plus gamma e to the j beta L. What we've done here is we've taken out V naught plus, we've taken it out to the outside, and we're just dividing to get V naught plus.
Okay.
This equation right here is very fundamental. You can see it pop up in many places, many equations.
Okay, I think I ended up getting negative 2.7 plus 0.9 J.
That is exactly correct. Yep. And then once I saw this, in this test, I was kind of like, oh, maybe I'm on the right track, right? Nice easy numbers, nice easy numbers. Don't be afraid if you get nice easy numbers, because it actually does help the work go along, so you don't have to worry about it. Okay, so now that we have V naught plus, what is the next step that we need to do for this small transmission line so that we can continue our work forward?
Okay. Real quick. I'm sorry. The V phasor of negative 0.5 lambda. What is that? I was trying to look around for that because I thought.
Oh yeah, sure. I'll scroll up back.
Was there one for that? Because I see the 6.5 for the 3 cosine.
Yeah. So I guess for the 6.15, this was in the original diagram. So this was assuming that the generator was at 0 and the load was at 6.65. But when we flipped our convention, we went back to the negative convention, so the load was at 0. What we did is we kind of figured out, okay, so if this is at 6.15 lambda, the distance from here to here is just 6.65 minus 6.15, so it's 0.5 lambda. And in our convention, we were able to find out the distances and flip them, and so this time we have 0.5 lambda right here.
Okay, so the 0.5 lambda is our previous 6.15, so that's just
Yep,
the 3.
Correct.
That is
Yep,
just-
exactly. Exactly, yep. Okay. And you should get in volts.
And the length is negative 0.5 then, right? It'd be 2 pi negative 0.5.
These links are actually already in. They've already taken care of the negative sign. So all negative signs here are all signs are perfect. Just enter L equals 0.5 right here.
Okay.
Wait, I entered a negative 0.5 though and got the right answer.
It might be. It might be possible. Let me check if I did that correctly. I did get this. I did get the same result, but I also may have just not written it down correctly.
I know yesterday Monty said that for the equations where we're getting the z input that involves the tangent and cosines, that those L's should be positive, but in the other equations that generally you're going to want to make sure to include that negative sign, especially in the one where it's you're solving for, I think, V naught or Vn, where it has e to the negative j beta L, and the negative j, that negative is explicitly separate from the negative in the L value.
So using negatives for the length, I got a different answer than the one I worked out, and I'm confident in the answer that this answer that you gave me right here, because I'm looking at my previous exam and that's the same thing I worked out, and I also worked this out in a MATLAB program as well too. So what I wrote out was, just so I can show you the work, V naught plus is equal to 3 volts over e to the j 2 pi 0.5 1 plus 1 over 3 I e to the minus 2 j 2 pi 0.5.
Yeah, and for me, with negative 0.5 or positive, I got the same result of negative 2.7 plus 0.9 j.
Oh,
So it's the same for
okay.
positive and negative for me.
Okay, then okay. Yep, I don't know if that'll affect somewhere in the future, like if that happens, but I would just stick with this sign convention right here. But I'm glad it works out the same. So maybe if there was a mistake, it wouldn't have affected anyone at that point. So the next step after solving this, after solving V naught plus, we have every idea of the transmission line. What is the way we move forward? How do we go on to the next transmission line?
Do we need to, is this where we find the combined impedance that they both see?
So that we will have to actually do that, correct? But what we can do, and what I did ahead of time, was because we're going to need a voltage at a location, we can easily solve it using, since we're going to need V naught plus in the next instance, what we can do is we can actually solve for VZM or VM. And the way we solve for VM, and this is the critical step that you'll need to go forwards or backwards if you're given a load at a certain location. So what we'll do is we'll actually equivalently write ZM as a generator or a source, and we'll have ZL here. And because we're not really concerned about the voltage, since we know V naught plus, we're not really concerned about what ZM looks like as a generator or a voltage source. But what we can do is we can write this as VG, or let's just call this VZM. And VZM is equivalent to, let's say, just VG, but I'll leave that out here. We'll say this right here is just VI, the voltage in, and then you'll have Zn plus Zg, and then you'll have Zn. Okay, well, we notice that we don't have a Zg here, so that goes away. And we notice that Zn, well, they're going to cancel. It's just dividing itself by 1, so it's going to cancel. So what we have is we have Vi at this location. And so what we can do is we can use the same equations that we've always used to solve for voltage at a location to solve for the voltage at Zm. And this is the critical step you move in and out of transmission lines, solving for the voltage at a load. Very important. So does anyone want to give me the equation that we'll use to solve for Vi or VZM? I'll give you a hint. It starts with V naught plus.
Where is it? I'm sorry, what are we looking for again?
We're looking for the voltage at any location in a transmission line. This is the first equation that, or not the first, but one of the equations to watch it tells you to remember.
Okay, is it the V naught plus e to the negative j beta z plus V naught minus e to the j beta z?
Correct. That is exactly it. That is exactly what we'll use. So we'll use this convention right here where my length is positive. And what is the length, by the way, that I'll put right here if I'm solving for the voltage at this location right here that we've previously discussed?
It'd be negative 0.5 or 1.75. I'm not sure which one of my diagrams kind of messed up.
It's okay. It should you said one of them. It's negative 1.75. That's the location we're at right there.
Okay.
And that's where the generator is, Zm. So I'll write that down right here. Minus 1.75 and then 0. And so we'll write 1.75 since I've already done the convention where the length is negative. And then we'll continue on writing this. So this is V naught plus gamma and then e to the j 2 pi 1.75. And then you guys can plug this into your calculator and get another answer. Are you guys getting this at this point? Just making sure. I know it can be a little bit complex, but
Yeah, I'm just trying to type it in carefully at this point.
okay.
Yeah, I think at this point, I think I get the general idea. I just need to do some more practice, and since he extended the test to next week, I'm gonna have plenty of time.
Yes, since he extended it to, I can't recommend this enough. How super important writing a program is to help you solve this. I had a program for this exam, and I didn't feel unconfident at all. I was very confident with every single answer when I solved it by hand and solved it in the program. Anyone else having any troubles? You can ask a previous question, or if you're still confused on something.
I had a real quick question about the program. For that, you just probably most people would just do basic formulas, or did they try to actually make it solve the problem?
Well, so this is quite funny. One of my friends from the previous semester actually did a MATLAB code that solved a problem, and it's based off this Excel spreadsheet right here. So this is the problem that we're working on right now. And I save this, and if I run it, it gives every value that I could possibly need in this. So I guess the voltage was wrong, but otherwise you could get any possible value that you wanted out of this transmission line.
Was it Luke?
No, it was Thomas.
Oh, okay.
Yep.
That was my second guess.
Yeah. There you go.
Yeah, I know
Oh.
Lucas wrote one to solve the problem specifically, and then he said in the test, like, having a different problem immediately just made his code useless.
Yeah. Okay, here we go. So what you should have gotten for Z0 plus, and then for the voltage at the load, VZM, you should have gotten something like 1.8 and then plus 2.4, 2.4i. I mean, I trust you guys can plug this stuff into the calculator. This is the equation that we all know and love, so.
I don't know about love.
Maybe. Oh, remember when you're writing stuff down, always put units. Very like small points that you can miss, but important points too as well, just to keep yourself on track on like what you wrote down. Okay. And so this is the most critical thing about this entire problem. We found the voltage at this load right here, and it's equivalent to the voltage across CM. Now what we'll do is we'll do what Jonas said, and that is what did you say that we're going to do, Jonas?
Oh, we're gonna find the impedance that both of those two things meet.
Yeah, so we're going to find like a Zn at that location, right?
Mm-hmm.
So that, okay. So what we'll do for that is we'll write out another transmission line. This is the outside transmission line, the one that's on the left side of the image, or excuse me, the left side of the picture. So we'll write out this. We'll just write out Z equivalent. And why are we doing a Z equivalent? Does anyone know why we're doing this? You don't have to like state the physics or anything, but just what makes it easier.
We're combining it.
Mm-hmm. Yeah, we are combining it.
Sorry. Yeah, we're combining it so we can work as one versus the parallel.
Yeah, exactly. Yep. If we have like a voltage equation that describes the voltage anywhere, we should have an impedance equation that describes the impedance anywhere, because it's just the relationship between current and voltage. So this is good. Now, does anyone know how we'll solve for Z equivalent at this equivalent load? There's going to be two terms in this, and then one of them we know, one of them we'll have to find. So I think, Mark, you already said what we're supposed to do, correct? You mentioned it briefly.
Yeah, bring them together so that it turns into one versus the parallel.
Exactly, parallel. So one of them we already know is ZM, correct? We know this one. And then this one right here, we're going to have to find out what this is. And so what term goes right here? What equivalent thing are we looking for at this location right here? Or maybe if you want to look at it right here, what are we looking at right there? When I know you're saying bringing them together, but how do we bring them together? What is the way that we can write out the impedance so that we can bring them together?
I'm sorry, I'm not sure if like this is right. I'm still like a little tired, but we have the two impedance at the end in parallel, so we should be combining the impedance of ZM plus the impedance at the load, right?
You're correct about half of it, but the other part is what we're missing right here. What we're missing is the Zn at this location. So we're at this location right here, we're looking for a Zn. And that is because when we find Zn at this location, we can reduce this down to a circuits problem, which is why we can combine it in parallel. Mm-hmm. So that's why we can combine it in parallel so easily without worrying about like the waves and stuff like that. So we'll find Zn at that location, and what's the length that we're going to find it at? What's the L or Z?
Is it 0?
It's the other one. It's for this guy, for this transmission line right here.
Okay.
At 1.75.
Correct. Yep. 1.75 exactly. Okay, and then we'll solve this Zn right here. Does anyone know the equation for solving the impedance at any location on a transmission line?
It's the big one with tangent or cosine.
Correct. And in this case, we'll use the tangent one because luckily this is not a 3/4 tangent or anything close to that. So okay. Anyone know the equation? Can they just rattle off the top of their head or look at their formula sheet?
I do not, and I have not made my formula sheet yet.
Okay. Anyone else?
We have Z naught times ZL plus J Z naught tangent beta L over.
Yep. Oh no, you can continue going on. Sorry to interrupt you.
It's okay. Over Z naught plus J ZL times tangent beta L.
That's correct. Yep, exactly. Okay, and then Z naught plus ZLJ tan beta L. Awesome. And so you guys can plug that into your calculator. If I were to mention anything that I hate missing more is this equation, because you always are given this, you always know this is true. I always know that I miss C naught consistently because I just want to type this part out, the hardest part, and then just forget the rest. And I always know it's like, why is it so small? I always forget the Z naught. So I would make sure that this right here is the first thing you write out rather than the long equation.
So Tawaja will always give us the characteristic impedance, right?
Yes, he should allow you to get the characteristic impedance. You can solve it, say you're given the gamma and ZL, and it should probably be lossless. I don't think it will ever be lossy or a lost line, but he'll probably give you lossless for sure.
Yeah, when we were actually giving our exam, like almost 3 semesters ago, he might give you all the R prime, C prime. He might give you the properties of the transmission line, and you got to calculate R prime, C prime, all the values, and if effectively you got to calculate the Z naught if you are given all those. So you got to learn how to do that as well.
Yep, that's correct, exactly.
And that's the easy question. If you get that kind of questions, you should be lucky because that's easy. This question does involve a lot.
Mm-hmm. Does anyone have a value for Zn? Zn at the location L equals 1.75. Any other questions you guys have right now at this moment? Concerned about any equation or any thoughts? Do you guys have a value?
I'm working on it.
Okay. And if you guys have the TI Inspire, I believe you could also do this with the TI 89. I don't know for sure, but I would set a letter on the calculator to the imaginary variable so that you don't have to go fishing through that menu every time you want to type the letter I or the imaginary variable.
That doesn't look right. I
What'd you
got
get?
40 minus 30J.
That's correct.
Oh, is it? Okay.
Yep. So
Okay.
all it just turned out to be was just a conjugate of ZL. How funny. You know, just 180 degrees or half off. So this right here is our Zn in the old transmission line right here. So Zn equals 40 minus 30 I ohms. In polar, that would probably be like 50, right? And then minus pi I or something like that. I don't know. Something, some phase angle. If you know the phasor or the polar, please say it. If not, you don't have to worry about it. So now that we have Z equivalents, or Zn, we can actually solve for Z equivalent now, which is our stepping stone part 2 to get to the next transmission line. So we can write Z equivalent as this. Actually, I'm glad you guys were able to figure out what Zm was. Hopefully you guys know that this is just minus 30 I or 30J. That really helps rather than typing in that polar stuff. So we'll write 1 over 30 minus 30J plus 1 over 40 minus 30I. And then when doing this, don't forget the inverse right here when you're plugging it into your calculator. It always, I guess for this, you should always remember that the value you should get should be smaller than your smallest impedance in this when you're doing this type of thing. So it appears it should be less than minus 30I ohms. Anyone get a value for this right here? Oh, I guess, let's see here. So I guess we won't have any more online classes until like Thursday?
Yeah, until
Wow.
the 17th, all types of classes are canceled.
Okay.
Wow. It's
Or I think
exams
through
are
the
also
17th,
canceled.
actually.
More motivation to study, right?
Yes, more yes,
Yes.
more time to develop code. Exactly, develop code. Yes. Oh, let's see here. Yep. Develop this code, the code that gives you every answer. Hopefully you guys should have been able to solve this. Parallel resistances, circuits 1. It should be in rectangular. It should be 6.92308 minus 19.6154, I believe. Let's see here. Somewhere right here. It's this one right here.
Yeah, that matches up with what I just got.
Exactly. Okay. Now, after we solve for Z equivalent, we're going to work with this transmission line. So I'll redraw it again because it's better to just see it right here. What is the first thing that we do when we see a transmission line problem? Because imagine we've just started a new we've found a new transmission problem. What did you say, Jonas? Cry? Cry, yep.
I thought I would heard it high, but yeah. Well,
so after crying, what do we after crying, we realize we're paying for this, so we at least maybe got to work at this. What is the first thing that we solve in a transmission line problem that you'll see mostly?
You want to get V0 plus, right?
Correct. Exactly. That's the end goal, right? Once you get V0 plus, you're done. But what do you want to do before that? What is the first thing that we did last problem?
We got the reflection coefficient.
Exactly. That is our stepping stone for this problem right here. So once we find this gamma, I'll call this gamma 1, just so to indicate the difference between it. Gamma, does anyone know the equation for this?
It's ZL minus Z naught over ZL plus Z naught.
Is everyone comfortable with knowing this equation? Does anyone have any differences to this equation? Like, I don't know it, or do you all recognize it?
Yeah.
Okay. And then solve this equation. What is going to be our ZL in this case? Anyone have an idea what ZL is going to be?
You're asking for the distance, or?
Sorry, ZL. Sorry, ZL. The load impedance right here.
Oh, that's the impedance that the equivalent impedance we just got, right?
Correct. Exactly. Yes, that is ZEQ. So it'll just be ZEQ minus Z naught over ZEQ plus Z naught. Awesome.
I'm sorry, I haven't eaten yet, so like I'm just like
No, it's
listening to
okay.
this and I'm trying to like digest this
It's okay.
without thinking about my stomach.
Yeah, now that you made me think about my stomach, I'm hungry too. Thanks.
You're welcome.
Okay, so we found our first equation. We know everything in this equation. We can solve for gamma 1 or gamma prime if you want to call it. So what does gamma turn out to be?
Z naught is 50, right? 50 ohms.
Correct. Yeah, the transmission line
Okay.
doesn't change. So
Yeah.
it's like using the same coax cable.
Yeah, using my store variables for ZEQ, I got negative 0.57 minus 0.54J.
That is exactly what I got. Correct. That's awesome. Good job storing your variables too. It's super useful when writing down this stuff. You have like so little time to do this. I think when I was working this test, I did it in the calculator, but I also did it by hand, and I was right up to the time. It was pretty close. Let's see here. Let me just make sure. Gamma is 3 ones. Okay. Okay. Now that we have gamma, what is our next step? You've already said this before. Just quizzing you again. It's always good to hear the thought process. Jonas, I think you said it, but maybe someone else can answer. What is our next step that we do after solving for gamma? Drew, what is the next step that we'll take after solving for gamma?
What are we trying to solve for again?
So yeah, exactly. So it's always good to read through. So we've been solving for VG this entire time.
Okay.
Exactly. So VG is over here, which is on this side of the transmission line, which is what we're working on right now, actually. So to solve voltage, right, we need something. So what do we need specifically?
V naught plus.
Exactly. And do you know the equation to get V naught plus?
Would it be the like V phasor of Z?
Mm-hmm. Yep. V phasor of Z divided by what?
Divided by e to the negative j beta Z plus gamma e j beta Z.
Exactly. Yep. That is what we're going to work with. Except what we're going to do is we're going to realize something very simple. Because we solved for VZM, which is in this case our load voltage at 0. What we can do is we can plug in a 0 for the lengths in that equation, and what we can do is we can get VZEQ is equivalent to V naught plus times 1 plus gamma. This is the equivalent equation that he stated, except that e to the j beta L is just going to, this right here goes to 0, which then makes this 1. So it just disappears into the equation. So now that we have our new equation, we can solve for V naught plus using VZEQ. So what we'll do is we'll rewrite this. And we'll do this 1 plus gamma. And this will be gamma 1, obviously, because we're in this transmission line over here. It might seem confusing what gamma you use. That'll actually be addressed, I believe, later in this problem. But for the transmission lines, when you're discussing the gamma for a ZM in this instance, let me just real quickly check what it is. I believe you use the reflection coefficient for the outer transmission line, or the one to its left, rather than the one to its right. I believe that's the convention for all these loads. I'll just check real quickly. It's somewhere this, right here. Let's see here. It actually, yes, it is for it's the one to its left. Always one to its left. Okay. Now that we have this equation right here, we can solve for VZEQ, or V naught plus, excuse me. And does anyone have this worked out already? So the value you guys should get for this, well, I'll remind you that VZ equivalent is 1.8 plus 2.4 I, or J. At this time, I was still using I when I wrote it down. I kind of like it. And we divide that by 1 plus our gamma 1. And that should give us surprisingly a nice looking value. Let me know if you guys get this. I got minus 1.1 plus 4.2 I as V naught plus.
Where did that equivalent voltage come from?
Oh yeah, so we'll review that. So I mentioned why we decided to solve for VZM right here. We wanted to solve it because it's our transition or our stepping stone between transmission lines, because there's a load blocking it. We solved for VZM using this equation right here, and we got this voltage value right here. So this VZM takes into account the impedance at that location, or the impedance at that location, and everything else you could possibly want for that voltage. And so by using that voltage, we can kind of transition into a different transmission line, and we can solve for V naught plus in another transmission line. So VZEQ is equivalent to VM, or VZM, which is equivalent to, in this transmission line right here, V at location 0.
Okay.
And because e to the j 0 is just equal to 1, you don't see those e's in that equation.
Mm-hmm.
This is also similar to like voltage at a load as well, so that may be where you recognize that.
Okay.
So after we've solved for V naught plus, using that equation, we'll then continue on our way to solve for VG, right? That's the last step that we have to do in this problem. And once we solve for VG, we can answer part A. And we've gotten basically every single part of this problem done. Everything that we've needed. So, does anyone know the equation to solve for VG?
That voltage divider one, right?
Yeah, exactly. It's that voltage divider. So, it's equivalent to Vn times Zn plus Zg in parentheses, and then over Zn. Okay. Since we know this guy, right? Since we know V naught plus, we can solve for Vn, right? You just have to answer yes or no. We can solve for Vn here, correct? Yeah. Yeah, exactly, of course. And then what else are we missing? Do we know Zn? Do we know Zg?
Yes.
Okay, so we do know Zg, correct? Yeah, that was given to us at the very beginning of the problem. 50 ohms. And we only have one unknown, which we don't know. So we don't know this, we know this. This is simply 50, this is unknown. So one unknown, one equation. And what is that equation that we'll use? We've already used it before, but we'll use Zn. Right, we'll use the Zn equation. Anyone want to state the equation again?
Z naught times ZL plus Z naught J tangent beta L over Z naught plus ZL J tangent beta L.
Correct, exactly. And two questions in this for this. What is L? That's the most important one. What is the value of L we're going to be using?
We're looking for the input impedance, so we're going to be using it for the furthest end. So it's the negative. What's the 6.65? God, my handwriting's terrible.
Yeah, so let's go back up here actually. So we're in this zone right now. So this is our second transmission line, right? But we've done something different here, right? We've set the voltage. We've set the value of the load or Z equivalent as 0, right? So what we next have to do is we next have to figure out what's this distance right here. Anyone know what that distance is or how to solve it? Well, what we simply have to do is we just have to take the difference in the values right here. So what you can do is you can do 6.65 minus 1.75, and you'll get 4.9. You didn't even need to take the difference because it was already given to you that starting at this 0, this length right here was 4.9. So that is our lambda. That is our length right there. So what we'll write is right here 4.9 lambda, and then we'll write 4.9 lambda right here. Lambda's already been taken. Lambda still needs to be taken care of, but because of the beta 2 pi over lambda, the lambdas will cancel out. So I'll let you guys solve this. You're solving for Zn. I'll just write down what I got right here. Let me know if you guys get the same answer.
Yes, that's what I got.
Awesome. Okay. Anyone close to getting it or getting the same thing? I hope so, because if you have any questions about this equation, please ask. I know you have a week now, which is good, so you have plenty of time for questions and answers.
Might I add, people that do have issues with it, there's a cosine sine version when the tangent messes up.
Exactly, completely. So in this case, we also got lucky again that the tangent worked. I was also part of that test that had that issue with the tangent, so I was upset, but I just learned, it is what it is. The program I have uses the sine and cosine, so.
Yeah, I always use the sine and cosine.
Exactly. I recommend that if you're going to program it too. Okay, this next step, we discussed what we know in this equation, right? Now we know Zn, and then we know Zg. Do we know Vn? We kind of do, right? We know V naught plus, but we don't know their value. So that's all we don't know, right? So let's solve for Vn. I know I'm drilling you guys down on the second time, but how do we solve for Vn? Or maybe this will spur your memory. How do we solve for the voltage at a specific location?
That phasor voltage formula.
Yep, exactly. So V naught plus e to the minus j beta L, and then you got 1 plus gamma e to the, let's see here, 2j beta L, e to the 2j beta L. I think that looks right. Does that look right to you guys? Or another way to write this is V naught plus, e to the minus j. 1 plus V naught plus gamma e to the minus, or e to the plus j beta L. Okay. We know beta, we know L, we know V naught plus. Super simple to solve. I can trust you guys are familiar with this formula. This is, very, very important formula. And I can trust you guys can plug it into your calculator. The only thing you guys need to know with this formula is that you got to make sure that you're using a positive length as well. So 4.9 lambda, you can cancel out the lambdas. You're just left with 4.9. Let's see here. Okay, so for Vn, we should get, I'm just kind of speeding up here, sorry if it's a little fast now.
It's okay, it's recorded.
It is recorded, exactly. Let me write this a little bit better. This is not good. 4.982 plus 4.292, 293 rather, I. And this is volts, very important. Always, make sure your units are sound. I'm writing down ohms here when I need to, writing down amps when I need to. After we solve for Vn, we can solve for Vg. I've already given you guys the formula we found the formula rather for Vg. So we'll just plug everything in we know. I'll leave that on the screen. And then Vg we can solve for. And then what you should get for Vg is you should get this. And when you're looking at the voltage in this format, it looks confusing, right? The generator voltage, some imaginary component. What the heck, right? I guess you could also think of it as the polar format, which would then give you the rise to a cosine, right? So you'd have this value right here. Say this is like 14 magnitude and a phase shift of like 2. You would just have that. It would be cosine of 14, or sorry, 14 cosine omega t plus 2 as your phase shift. So don't get confused by this right here. I've written it down as rectangular because my program gives it in rectangular. So have we solved this part, right? Have we gotten the value that we've wanted? Do we need to do any more calculations regarding VG or anything like that? I'll go back up to the original equation. It looks like we don't, right? It says it's the phasor. It gives us the tilde above the phasor form. So this right here is our final answer for part A.
Woo.
Awesome. Next part B, we'll go look at that right now. Part B asks us to determine the power delivered by the generator. Luckily, we found the generator voltage, right? So what do we have to do now? We just have to determine IG. And we'll write out the power equation for that. And then let's see here. Then part C asks us to determine the reflection coefficient. We'll get back to that after the power. So for part B, we'll solve for the power delivered by the generator. This was given by Susav earlier as the real part of VG times the conjugate of IG. And I kind of got messed up multiple times in my first exam with, like, oh, what's the IG? What's IG? And I was thinking, I didn't recognize it at the time, but it simply is just a voltage divider, or it's not a voltage divider, but it can be drawn out as a voltage over some, sum of impedances. And so I'll draw that out right here. I believe Easton discussed this last time when they were doing their review. It was pretty good. And what I've drawn here is a circuits 1 equivalent of the transmission line. So this right here is Zn. Okay, Zn. We've already solved for that. And this right here is Zg. So we can imagine that everything in this circuit is taking place at a small point. So there's no effect of the wavelength. And what you're solving for is you're just solving for the current I. And that's all you're solving for right there. So we all know V equals IR, so V over R equals I. I'll rewrite PG as what you would type into your calculator if you have a TI Inspire. Type the real of this. VG, I won't type actually VG itself. Conj, this is super important right here, conjugate of VG over Zn plus Zg. I'll zoom in on that right there. This will take care of everything right here, of the conjugate of everything inside of that. And this right here is equivalent to your current IG. And then the conjugate makes it the conjugate of IG. So what is maybe you guys have already plugged this in, I don't know. If you guys get this value right here, do you think this is correct? Or do you think this is wrong? PG as this right here.
That looks similar to my homework stuff, so I think it's correct, but
yeah, this looks, it looks very small, right? The voltage delivered at the load, delivered at the generator. But we also must recognize too that the voltage here is probably, not that much. I don't know what the magnitude of that is, but let's see here. It's probably maybe not even greater than 20 or something like that. But I couldn't imagine how small that is. But of course, you also got to consider too the equivalent input impedance. I know Sustav was talking about when you were dealing with 100 volts, source or generator, that if you got something around like 0.142, that obviously looks very wrong. Like it's 0.14 watts being generated by the generator. No. But for this, I don't know if I didn't have my program, if I would have been scared by this, but I think at some point I would have just had to accept, whether right or wrong, that this value was correct, because every step I took before that was also correct. I didn't know at the time, so I just had to live with it. So okay. If you have any questions right now about how to get the power, or if you're still confused about the power or input voltage or generator voltage, ask right now, and we'll move on to the next.
I'm about to head out of this review, but I just wanted to let everyone know that I posted not the exact work that Monty was writing out during review 1, because towards the end she wasn't writing out a lot of the work. She was making y'all solve it because we were getting tired. But all the work I did for that problem and the actual exam and her important equations are in the files section of this Teams now.
Awesome, thank you.
Okay, thanks.
Awesome, thank you. Good luck. Have a safe day. Safe and warm day. Okay, so now after we solve for PG, what we're going to solve for next is the reflection coefficient at this location right here. So this is in our old convention where positive distances rather than negative. So can anyone tell me which side of ZM that reflection coefficient will be? The right or left side? That's all you got to say. One or the other. Let's see here. So it obviously should be the right side of the picture, of course, or right side of the ZM, because we're dealing with values over here. And we're not on this edge right here. And if I mentioned on the edge, what you'll do is you'll actually just consider the reflection coefficient from the left side of the load. But since we're not in that case, we don't have to worry about that. So we're focusing on this gamma right here that we found. So all you got to do is just go back through your work. Oh, look, there it is right there, the first thing that we solved. Isn't that awesome? Isn't that awesome? The first thing that you solved is the last question, right?
Yeah.
10 points, though. I mean, it's very useful 10 points. So for part C, what we'll write is gamma at, let's see here, 6.15 lambda is equivalent to 1 over 1/3, or 1 over 3 I, or j, which is equivalent to j 1 over 3. And we'll just note that this, in our transmission line, our TL, it was L equaled 0.5, minus 0.5. That's what we had. This doesn't have any units right here, so, and that's the problem complete right there.
Uh-huh.
So this
Awesome.
looks very similar to, I believe, the example that Tawacha has given y'all. Is that correct?
Maybe, I think. I don't really remember.
So, okay, so I believe this first question looks similar because remember T was asking for the values that you guys were finding. So, T, did you work any more on the example from Dr. Tawacha?
Yeah, so he gave out the retake from last semester, which is what the test that you're doing right now.
Okay, so let me see here. I have some values if you want to discuss them right here.
Let me see.
And for anyone who's listening to this recording and watching it, I stopped sharing my screen because I mean, I don't want to give you guys the work for it, but if you need any questions about how do you solve it, watch this lecture, of course, again, and review what we've said. But if you have any questions, Susav, Easton, Monse, and I can also help you out with anything on this. Okay, so I'm ready for the answers.
Oh, I think he's actually give out test 1A.
Yes, I do have test 1A. I did work that out.
Okay. Let me look through it real quick.
Mm-hmm. Also, would you guys like me to post my work that I did for this problem?
Sure.
I mean, I'm happy to, right? It's just a review. I'll do that right now. Okay. Let's see here. Okay, I'll also add it to this team's files as well. Let me do that right now. Are you still looking for the papers, T?
Yeah. Is it possible if I text you later?
Yeah, sure. Yep. You can text me later. Also, anyone else here can text me later as well, or message me on Discord or Teams or whatever.
Okay, that would be great. Thank you.
No problem. Okay. If you guys
for
have,
that review.
yeah, no problem. If you guys have any more questions, message me on Discord or Teams, and I'll be able to help you guys.
Oh, hey, Nick.
Yeah.
I do have one question about the lab we just finished.
Yeah,
Do you know where I could? Huh?
Yes. I'll just stop recording so that we don't go on for too long. Okay.
Okay.
Yep.